we are very happy to have Tolga here with us. Tolga is a professor, assistant associate, we don't know, professor at Imperial College London. And he did his PhD in TUM with Nasir Nawab, and then he moved to Stanford for his postdoc. Tolga has done amazing work in topological machine learning and 3D computer vision. If you probably worked on point clouds, it's impossible not to hear his name. He publishes on top-tier conferences in our field, both machine learning and computer vision. If you go to one of these conferences, you will probably run into him. He's usually part of the fun meetups, organizations like it was at NeurIPS last week, not last month. Tolga will talk about topological deep learning and new hope for AI4Science today. All the stage is yours.
Thank you. Thank you. By the way, last week was my birthday, so that's
Happy
why
birthday.
it was also like a special organization.
I missed it, but I had a celebration.
Yeah, I mean, I'm really excited to be with you guys because, like, with some of you folks, we worked together, and I never had the chance to interact physically beyond conferences. So it's actually amazing. Like, amazing. Thanks for the invite. Okay, so we started this effort with a bunch of people. In fact, so there were, I think, in the original paper, 14 authors or so. I didn't put the link of the paper, which is a shame. But sorry, I can send the paper link. I think you have it in the invite. We collaborated on this with a bunch of people from mathematics and computer science. Some of them are great in topics like equivariances, so they work in mathematics on representation theory mostly, and some of them are great in topology, and some of them remain in geometry and and so on and so forth. And I don't know what I'm good at, so I'm like anywhere in between these guys. The core effort has been led by Mustafa, Nina, myself, and Gada. And I'm Michael. And we are right now trying to organize a lot of workshops and trying to put a lot of effort on this topic. And this is actually the second time I'm talking about this. But last week I learned that our CVPR workshop has been accepted. So I think you will hear way more on this. So unfortunately, I will be using the board a little bit. So I'm very sorry for the folks in Zoom.
They can see it.
They can see it, hopefully.
See it through your camera.
Okay, good.
Also,
So if you want to switch to my camera, that would be okay. So what do we want to do in machine learning most of the time, right? So here is what we stupidly want to do. So we have, let's say, a universe of machine learning models. We usually call this the hypothesis class. Set of all hypotheses possible. These would include different architectures. So part of this hypothesis class would be, for example, SVMs. A part of this would be, I don't know, GMMs, whatever machine learning model you work with is in there. And think of this giant thing, infinite size. And then here in one corner, there is deep learning, which we all do now, right? So deep models, I should say. And this class, we usually have architectures. So most of it is composed of, let's say, different architecture. Let's say this architecture spans this region, and then there's another architecture that spans this region. So you have a bunch of possible architectures, in fact, possibly infinite. And within each architecture, you have the model parameters. So you change the model parameters, you get another hypothesis, right? So imagine this huge space. Now, in that space, let's say you are doing deep learning, right? And you specify yourself to a certain architecture most of the time, which is a bad idea. But still, you start from a point here because your weights are randomly initialized. Let's say data zero somehow comes from some kind of an interesting distribution. And then you want to find your way to this, hopefully the best model you can find that will fit your data perfectly, right? And this is a challenging problem, as you all know, because the number of parameters in your model is super large. And there are all sorts of caveats. Maybe your loss function is not modeling the reality correctly, and so on and so forth. There's the generalization issue and whatnot, right? And so what you want to do, you want to put a lot of inductive biases. And what are the inductive biases that we actually put? What do they do? So they, in fact, restrict the possible hypothesis class, right? So what you're doing, let's say, instead of starting at this point, if I impose some kind of a constraint on my variables, then maybe I will be starting at another point, and then it will be easier to move. So let's say I will maybe restrict the region such that the best model remains inside this region. But I can only do this as I see the training data. And as you see on the slide, so for example, there's this population loss, what people call the RF. Okay, this is usually an expectation, so usually an integral, that's population loss. And that is saying that if you have all the data in the world, if you have seen everything, that would be the loss you attain. Okay, and that includes, of course, your test data, your training data, and all sorts of other data that you could possibly see. And then there's the empirical loss. That's the empirical risk, right? And that empirical risk is some kind of an estimate, R, given that hypothesis. So, and to get that estimate, you sample randomly a batch of data, or you collect a batch of data, and then you evaluate this loss function. So to train, you need this training data. So what you have access is this. You never know what that is. Okay. But you hope that just by training on this, using this risk, you get some kind of a, well, just by training, let's say, on a finite set of data, you get an empirical loss that is close to the real loss on any sorts of data. Okay. Well, again, challenging problem. So to make that happen, you kind of want to put a lot of price. So you see that this is uncompletable, by the way. And you know, some kind of a supremum of this, or people do it different ways, can be linked to a generalization, what is called the generalization error, right? So basically what you train is this, but at the same time, you want this quantity to be small as well. And so that's a paradox in deep learning. So this is what the end of machine learning people work on. Of course, you know, what type of priors do we have? Like, or what type of regularization do we have for data, right? One is, for example, that you will know, I assume, or I'm going to force my weights to be Lipschitz, or I'm going to force some kind of a weight decay on this. Or I'm going to say it's a, you know, or whatever, there are Sobolev norms and things like that. But at this stage, you know, geometric deep learning was introduced, and it said, well, I know a lot of priors about the world, right? I know what I'm looking for. So if I'm trying to solve for certain variables, let's say I'm trying to solve for an angle, I know what an angle looks like mathematically, right? If I want to solve a rotation, I know what a rotation looks like. So I'm going to bake these transformations into the network to get better inductive biases. That's the first thing. The second thing it said was to decompose the domain from the signal and the transformations that act on this domain. So basically, if the object is being rotated, and if you still want to classify the cat as a cat, right, then you want to do this decoupling or disentanglement of these things, not like a CNN. In fact, this typical CNN would have implicit separation of these things, and it would be, for example, translation equivariant, right? But you could think about other forms of equivariances, right? And by that, your domain, right, which is usually for an image, for example, it would be the pixels, the arranged in a grid, in a lattice. But then they suddenly realize that this can be anything arbitrary. So this just looks like a graph, and I can in fact choose it as a graph. And since my representation of the transformations are disentangled from this, now I can have some kind of a nice mathematical framework for processing graphs in an equivariant manner, and that was known as geometric deep learning. And there's a book called 5 Gs of GDL and so on and so forth, right? And then you try to design models that take that into account. Okay. Now there are, unfortunately, some problems with it because the data domains, although GDL spans a nice spectrum of data domains, it's still a little limited. Okay. That's because we really have arbitrary data domains, and some of them are not graph representative. In fact, GDL is really good when you know that the underlying structure is some kind of underlying object admits some kind of a global structure. So let's say the sphere can be discretized into a graph. You still know the global structure of this, or the image itself is maybe a continuous plane, but I can sample points on it, and that's going to be the pixel grid. Yeah, and that's really good. But the most widely used structure, which is a graph, does not have such a global geometric model. And then, sometimes, of course, you want to do things locally, but it's also very hard, in a continuous way to assign charts locally at times. Okay. So instead, we switch our attention to neighborhoods and open set structures. That is how the topological considerations begin in this book. You look at the graph, any graph, and it looks like there's kind of a little neighborhood, a discrete neighborhood around it. Of course, if you kind of increase your resolution, you go finer and finer, you end up in some kind of a continuous neighborhood. So why we do this is there's a reason for it, because we would like to model, and I will talk about this a lot, higher order structures. So when I say this, by the way, who understands what that could be? And I'm asking this for a reason. Anyone? No, right? So because this is something we generally ignore in a lot of machine learning problems. So usually we work with a graph, and we quite believe that the graph is a beautiful representation for anything in the world. Social networks, right? The images itself, the image itself, or anything, the traffic flows and everything, right? And then we use graph neural networks for this. So, but let's look at a very basic structure. Let's construct, for example, our social network. I will just say here at this node is a mother that is in some kind of a relationship with the father. Right? And as a result of this beautiful relationship, they get a son. Okay? Now, son is, of course, connected to mother in some kind of relationship, and also connected to father, whatever their relationship would be. But now these three entities come together, and you suddenly call this a family. And why do you call this a family? Because the relationship of these three things, of these three people, aren't just the relationship, these pairwise relationships put in a bag. They form this kind of new relationship that is a family, that is actually the inside of this triangle field. So any single social network you think, well, by the way, triangles with field structures cannot be represented by graphs. And so anything, any social network is apparently not a graph. And you can think of other things. In fact, this is true for almost anything. Let's say you start playing music, and you kind of play the guitar, right? And then somebody comes, the bass guitar comes, right? And the bass guitar is playing in tune with whatever you are playing, so you are kind of synchronized and you build a relationship. And then the drums come, and it's also in the kind of in the same metronome. Now, of course, is in tune with bass, is in tune with guitar, and you kind of suddenly have another new relationship. So you just generalize this to everything. And it's in fact known as the synergy. Right? This is a result of synergy. And synergy says the sum of the parts or the whole is larger than the sum of its parts. Right? So you fuse these pairwise information, and suddenly you get an information that is not contained in any of these relationships.
So, Tolga, what about hypergraphs? So, can we treat
So,
this
yeah,
like a
so this
hypergraph?
for now, this sounds like a hypergraph, and thinking as a hypergraph is perfectly fine for the moment, and I will touch upon it later. Okay, so you get the idea that now we would like to model these structures. I mean, this is contained in the data. It is not that that we don't have it. Usually, simplifying this to a graph, you kind of lose information. You neglect that information for the sake of computationally tractable processing, for example. But we don't want to do that. We actually want to keep these relationships, and for example, hypergraphs would be one way to do that. But I will come in a second why this wouldn't be the case. So there are all sorts of other mathematical objects in the world, and we would like to have possibly some kind of a mechanism that does not distinguish anymore these structures and is truly universal today. Okay. By the way, one easy example for computer graphics people, if you look at meshes, for example, meshes are not graphs. Meshes are composed by triangles, and triangles themselves are actually meaningful, right? Or triangle meshes at least. But or tetrahedral meshes are composed of tetrahedral elements, and they are meaningful by themselves. So in that regard, for now, even in 3D vision, what we have a point cloud, right, which is just a vertex. Okay, we have a graph, which is vertex and an edge, and then we have the triangle, which usually has the notion of vertex and triangles. This is how you would store it. But I would say there is usually a common misconception, because we consider the triangle as something that connects three vertices. This is not really true. A triangle actually connects three edges, because well, there is a flow from this edge, because the triangle is filled in. There's a flow from this edge to this edge without touching any vertex, right? And vertex is just kind of the endpoint of that edge. So, at least topological speaking, and this happens a lot. For example, in practice, like if you want to model particle interactions in fluid dynamics, or if you want to model how a cloth, if I pull this, how it's going to deform. Well, it's not that vertices interact and they kind of result in some kind of dynamics, but it's rather how the states of individual edges affect the state of other edges, right? So there's an edge-to-edge impact that is impossible to model with a graph, because graphs model vertex-to-vertex relationships or node-to-node relationships. Kind of binary. And then comes the applications in science. So, for example, if you would like to model proteins, well, you could go with hypergraphs, but hypergraphs are kind of, they encode these set type of relationships, and they totally lose the meaning of individual cells. So the moment you abstract certain nodes to a hypernode, what you say is, okay, this hypernode is just a node. I'm just going to treat this as a node, although it is really at a higher level in a hierarchy. So the moment we do this, you kind of lose the meaning of what certain proteins would be. People came up with different things. For example, they came up with simplicial complexes, right? And you see there, but they have a limited representation. There you see that they represent the triangles only at this part, and then these triangles, of course, are not everything. They are not the molecules themselves. Or you could go to something called a cellular complex, which would go beyond triangles and have faces that are non-triangular, so polygonal faces and so on. And this is more expressive, more representation power, but also not completely faithful. So we introduced something called on the right hand side combinatorial complexes, which are really combinatorial structures. That are like hypergraphs, but preserve the ranked structures, and I will talk about this in. So, of course, why we would do all of these things, right? It's a big problem, for example, in today's world, that we would like to do drug discovery. Everyone is working on this problem, and if you follow the nerves a little bit, it's proteins everywhere. So what happens is you have K drugs, and then there is like some binding sites. I don't know. So there could be some virus, or there could be some molecule that you want to attach to, and then you really would like to predict the sites, the sites, and their effects on this, kind of protein to drug interaction space. Okay, and this space is actually really a higher order. It's the relationships of relationships that count, and not just the pairwise relationships. So if you want to model cognition, so if you want to look at the areas of the brain that are responsible for higher level cognition, we in fact see immediately that there are, so this is, I did not cite it, but comes from a neuroscience paper, and we immediately see that there are activations across. So also, this happens also in a neural network, by the way. So the neurons that fire together, they belong to different regions of space, and they create these higher order elements, right? And in fact, you can gradually see this. So the low-level tasks, such as auditory processing, are occurring in these, they say sub-circuits that look like graphs, because these are low-level tasks at the moment. You complexify the task and you go to higher level cognition, you see that there are jumps across regions, and then things that fire together are really interesting and cannot just be simplified to graphs. And people have been doing that in neuroscience for years, and in fact, it's like 2021 paper, but now it's coming more and more, that they want to do higher order modeling for understanding how brain functions.
So in this case, what is the precise complex that you consider? If you have like n neurons firing together, then they form an n simplex. Is that the?
For example. And I mean, in fact, what happens here is you have n, which is a very large number of neurons, and then you have a stimulus, and then you kind of look at how the neurons activate for different stimuli. And you see that there are certain patterns that some of them kind of activate together, right? And the things that activate are in kind of stronger relationships than just pairwise relationships, obviously. And in fact, this order is really high. Another good part about having access to higher order structures is when you have a graph, let's say, and you want to message pass. You want to pass information from one point to a distant point. And when you do this in the graph, right, for example, Michael Bronstein always works on this. What happens is over-smoothing and over-squashing. So it is you kind of gradually pass information along the layers, or to different nodes. You kind of smooth that information, and this is a problem. And this offers a very easy fix to that. Of course, by increasing the dimension, at the cost of increasing the dimension. So you kind of make up this higher order cell, and instead of trying to pass information along edges, you pass the information from every single vertex or edge to this higher order cell, right? And you aggregate the information within that higher order cell and pass it back. If you do that, the effects of oversmoothing are greatly reduced. Okay, so I will also check the time.
It's just one level of hierarchy.
What do you mean?
Can be multiple
Yeah.
levels of.
Yes, I will. So, right. So now you see my goal. My goal is to kind of generalize the traditional domains of point clouds and graphs into general topologies. And what you can do is you could use of course, the traditional domains are the discrete domains. These are point clouds and graphs and meshes. But meshes, this is strange because people were trying to find mesh networks just by themselves. Like there is this mesh diffusion, mesh net, mesh conv net, whatever, right? All these architectures. And the reason why they are trying to learn on meshes is because meshes are not graphs, and they want to come find these better architectures. But now, let's forget about this. You want to find something more general. I don't care if it's a mesh or an even higher order structure. But while doing that, I do not want to lose the hierarchical information. So if I say that I'm at a certain point of hierarchy, I would like to know that. So a hypergraph would ignore this. So we kind of want to blend the space of complexes that mathematicians or topologists know very well, by the way, with the world of hypergraphs. And by doing so, we would like to architect some kind of a deep learning on this. Like there's a data domain, which I would model as a topological space. And then I would define a lot of operations like convolutions and pooling and attention and whatnot on this, and message passing in general, of course. And then in the end, you have your final task, loss function, whatever you would like to achieve. The interesting part comes here, I think. That's a little hidden, but it's like a crux of it. If you do that, if you can really do that correctly, you could pass information from edges to vertices, edges to triangles, vertices to triangles, or so you see, like, think of this as a message passing scenario. In a graph, you would pass message from this guy to this guy over the edge, right? But now you are given a higher order cell, which is a triangle that is kind of an inner meaning. And now you could actually pass information from this edge to this vertex, from this edge to the other edge, from this edge to the triangle itself. And these are all meaningful elements. And this is happening during message passing, for example, and that means you can share information in all sorts of interesting ways.
Are they different types of messages?
For us, no. But I can imagine that these messages are distinguished. So just like there's a blueprint of geometric deep learning, let me also give you a blueprint of deep learning. And this kind of summarizes what I have talked about so far. So first, you start with a set of elements, right? That are independent of how the relationships are constructed. And then you have to kind of construct a neighborhood structure, which defines how the relationships are made. It's the second stage. The moment you do this, now if our framework is general enough, then you are in the setting of graph-like learning, which means that you can use these strange neighborhood information to pass messages here and there. And then you define your message passing, and in the end, of course, you kind of define your pooling operations and stuff. So you increase your receptive field size and apply all the deep learning stuff that you know. Okay. So again, the idea is to unite the higher order domains and the domains of geometric deep learning, and come up with a new structure that would rule them all, and then define a neural architecture.
I wonder,
Mhm.
you're increasing the number of nodes edges in the traditional sense, like crazy, right? Like, is it too early to worry about computation?
It's a bit early to worry about computation. No, I mean, there are ways to sparse, just like you would sparsify a graph, you would also sparsify it. You wouldn't just consider every single higher order cell, but you would consider the ones that are critical and stuff like that. But it's a research topic by itself, nice. So, okay, so the differences, like as you see on the slide, there in the graph, you have this bipartite relationship between the vertices and edges, right? So you can think of the edges as a set, the vertices as a set, and then the graph will define this, connections, and you specify which vertex is actually a part of which edge. Now, if you have a hypergraph, you could do the same, right? It's just that now your edge set is kind of a little higher order, and then is these hyper edges. You can connect your vertices to these hyper edges. In a cell complex, and this is what I really mean by the hierarchy itself, you kind of have this intermediate type of intermediate layer where everything gets connected, which is called a cell, and then you go to two cells. So this hierarchical information is kind of preserved in what is called a cell complex. Okay, so let's say 1, 2, 3 is actually a part of a triangle that you see there, and then 2, 3, 4, 5 is part of another cell, but at the same time, 2 and 5 share an edge, for example. So it's hierarchical structure. Now, in what we offered, you see that now suddenly there are these edges, and they are colored differently. And different color means that they are living in the different level of the hierarchy. Right, so 3 is a rank 0 cell, which is like a no connection, and rank 1 cell is basically connected by an edge. Rank 2 cell is like a triangle. Of course, you don't need to think about this as a triangle. You can think of an abstract relationship of the elements 1, 2, 3, and then just like in graphs, you could speak of some matrices. These are known as boundary matrices, but in graphs, you would, for example, have an adjacency matrix, right? That would relate which vertices are neighboring. Or you can have other type of matrices. For example, you could have a matrix that has edges on one dimension and the vertices on one dimension, and then specifies which vertex is part of which edge. And all these matrices are quite typical for graph structures. And you define your convolution operations, message passing operations using these types of structures. For example, Laplacian, the graph Laplacian would be an essential object that you work with in graphs. So, right, and here there is this the k-partite structure is kind of broken by including these edges from rank 0 cells to rank 2 cells, kind of. Right. I'm not sure if I should do this, but I think I will. Just for a second. Okay. So I will define this a little more mathematically concrete. So I will speak about this combinatorial complex CC as an object that is a triplet S. Here I call it X. And the rank function. And then, well, yes, so this is my set. Okay. This is basically the elements that I have. These are just the nodes. And then from this, you can think of the power set, PS. I don't know power set. Everyone knows power set. So, of course, power set represents all sorts of relationships that you could have given nodes, right? Because it's going to be contained of multiple sets that specify all sorts of pairings and or quadruplets or whatever of the elements in S. Good. Now, my X will be a subset of this power set. So it will specify only a certain part of relationships. So this is sparser than the power set itself. Right? So power set is a complicated one. Okay. And now, so if I had actually these these maybe two things, I might be talking about a hypergraph. But now there is a rank function, okay, which is defined as kind of it specifies these inclusion relationships. So let's say if X and Y are two elements of X, okay, which is subset of PS. Well, I also ignore the empty set, but you know, never mind. Now, if X is included in Y, because these are sets, right? Because they are part of X, then that means rank of X should be less than or equal to rank of Y. So this is basically saying, for example, it's quite easy to understand. So vertex is a rank 0 object, right? And that vertex is contained in this rank 1 object that is an edge. Okay. So since that vertex is contained, that means its rank should be smaller than the rank of the edge. So this is building up an actual hierarchy on the topics. Okay, so and combinatorial complex is this. So I want to define some best spacing operations on that one. Just so that you understand. So there's a very nice mathematical description of this. And you can see examples of it. Right? You can even do an exercise, right? So there is my set is now S is S0, S1, and S2. Okay, and now you specify by some kind of an X the relationships between them, and obviously you see in the first one, for instance, the S0 to S2 relationship, for example, is not included. That means that we are not spanning all the relationships that right, and similarly for all the other for all the other things, you can see that there are now edges that are not contained in any higher order face, and there are higher order faces. Well, there are faces that have order higher than 2. For example, in C.
What is the advantage of taking a general rank function rather than taking, for example, say, rank of X being equal to the cardinality of X?
Well, you specify. You get a generality in the sense that you can specify different kind of rank functions, and it becomes an art form to choose your rank function, and then you can devise more interesting packages. It's related to orderance currently. Okay, so good. Let me go to this. So the neighborhoods, right? There are higher order. So what I'm covering here is the higher order neighborhood structure. So if you have a point cloud, as you see on the left, and you see that there's a red point, which is like the center point of that local neighborhood maybe. If you were to do it in the typical sense, if you were to do a point cloud processing, you would, for example, retrieve the k nearest neighbors and then connect this point to each one of them, right? And then you would say, okay, this is like the neighborhood is whatever points would remain inside a certain epsilon mode. But now you can have a structure that has the edges as well. So your neighborhood is defined by the set of edges, let's say remaining in the first hop or the second hop, plus the set of vertices. Now you can go beyond this, and you can have triangles now. And now your neighborhood is composed of, well, all the kind of, well, right. So all the triangles, and then the points, and then the edges. Now, you want to, of course, define this in kind of a unifying way. So what you say is, let's say, you define some kind of a K neighborhood, right? Which is the neighborhood of rank K objects. That's the neighborhood composed of only rank K objects, so just the vertices. Or the one neighborhood, which is just the edges, set of edges, and then set of triangles and so on. Right? So now your neighborhood structure becomes interesting. And then you would like to communicate these things. So this is me trying to abstract away a lot of technical details, but you could easily imagine. In fact, let me do it here first. So let's say you have whatever you see down there is like a simple graph-ish thing, and with faces. And the faces, you see that these are oriented faces. So you know from which vertex to the other you go. If you had a mesh, for example, this would determine the orientation of the surface normally. But ignore that for the moment, think that they are oriented. So now you can think of these boundary matrices that relate rank 0 elements to rank 1 element. Rank 1 element is an edge. So now I'm relating in delta 1, so the boundary matrix 1, the vertex 0 to the edge 0 and 1. Is it included? Well, yes, it is included. And how is it included? Is it is it in the direction of the specified orientation or in the opposite? So you can specify such a matrix. And likewise, del 2, you could specify well a boundary matrix from edges to triangles now, right? So from the edge 0, 1 to triangle 0, 1, 2, 3, 1, 0, 1, 3. Okay. And then you encode. So these are the matrices you work with, actually. So these are like the boundary matrices. And if you encode these matrices, actually, you could define what is called a K Laplacian, or equivalently, people call this the Hodge. If you ever heard about this Laplacian, the Hodge Laplacian, which is this interesting object that is so BK is a neighborhood matrix that goes from K to K plus 1. Okay, and so right, and then so or sorry, K to K minus 1, and then the K plus the BK plus 1 goes from the cells, the K plus 1 cells to K cells, right? And then if you do this simple linear operation, you end up with a Laplacian matrix that is aware of the rank of the coordinates. Okay, so that's a rank-dependent Laplacian. So you know in which hierarchy level that you are working with if you have this object. And interestingly, when you have a Laplacian in the graph, we take its eigendecomposition, eigenvectors, eigenvalues, etc. And they give you hints about the connectivity structure and interesting structures about the graph, right? Or how I don't know, how connected or how sparse it is. Here, the eigen properties, I should say, or spectral properties of that object gives you an idea about the holes and about other kind of topological properties, like relates to Bethe numbers and so on. And for such a simple complex you see on the left, you have this type of a Laplacian matrix. Like this is L up and L down, and your Laplacian is basically a sum of those. Good. So now we define the neighborhood structures. There's this one last thing to do. How do we do message specifiers? Because now I just talked about a K neighborhood, so rank K neighborhood, right? So there's a neighborhood composed of vertices, there's a neighborhood composed of edges and faces and so on. So what you do, you just gather those neighborhoods individually, and then you do a within neighborhood aggregation. Means you do just the vertices kind of aggregate a message in themselves. The edges aggregate a message in themselves. And then from these different neighborhoods, you once again combine the information in whichever way you want to combine. And then you come up with the final message. Right? So just like in a graph, but we kind of defined a rank K or rank array message passing scheme. And mathematically, it's also quite simple. You just, instead of one aggregation, you can do two aggregations within neighborhood and across neighborhoods.
When you group them according to semantics like this, like vertices together, edges together, are you ignoring some locality which is very important for example, representing three shapes? Like vertices, close edges, communicate first kind of structure. Doesn't it make more sense in terms of shape representation?
Vertices and edges communicate.
That is spatially nearby, right? Like vertices and edges are there.
But you do that, right? So this type of a neighborhood is like, there's again a special neighborhood.
But all the vertices, it's very global, right?
But if you increase your local neighborhood to a very large epsilon, it also becomes global.
True, but they don't talk to any edges, for example. Nearby edges become less important than a faraway node in that sense. You see what I mean? I talk to faraway nodes first as a node rather than a nearby edge
Yes.
in this hierarchy. Isn't it helpful for local shape representation? I'm thinking like
No, you talk to the nearby edge rather than distant vertex, yes.
but you group vertices together, you group
But
edges
the
together.
vertices are also grouped of.
Yes.
Okay, so again, simple operation. So now we have to do unpooling, and I find this very remarkable. So pooling operation, whichever domain you use, or whichever domain you are in, is a higher order message passing. Even the image pooling. So what you do is you have your grid, you have your pixels, let's say, as you see here. Okay, and now you just invent these higher order cells, the blue ones. The blue ones, I'm just image pooling here, by the way, as an example. So the blue ones, I just introduce them as higher order cells that kind of relate a larger or a more interesting neighborhood of the image. And now I pass all these messages from these individual pixels to this higher order cell, and then aggregate information within that cell, and then pass it back. Now and if your aggregation is, let's say, the max operation, then you kind of recover max pooling, because whatever remains inside this new higher order cells is the information, is the pooled information you compute. So pooling is very natural. You just need to introduce this additional dimensional traces and then pass information. Good. So far I just covered message passing and pooling, and unpooling is also similar. And you can, I think about more operations, and we are still developing further deep learning operators on these things. Well, you can also get a very nice tensorial representation of this. Here, each color is a color given to a rank, and then you can draw your diagram very nicely as information transfer from these between different ranks. Okay. We put a lot of effort on this. I mean, it's a crowded team, so we were able to develop some kind of a nice software package. In fact, 3 packages. One is called TopoModelX, TopoNetX, and TopoEmbedX. So TopoNetX is like HyperNet. So it's the basic structure to work with any like simplicial complexes, cell complexes, and combinatorial complexes. Even hypergraphs, we have some support. And then TopoModelX or TopoEmbedX is the library of these deep learning operators that we developed. And TopoModelX are actually the actual practical models that we developed to solve different tasks. So for example, well, and then we organized this ICML challenge in topological deep learning. And a lot of people submitted a lot of interesting implementations. And they kind of contributed to the package. It's growing slowly but consistently, I should say. And this, thanks to this nice tensorial representation, you could visualize your architectures in quite simple ways, a little abstract, quite simple. And these are just some models that we already have. We don't have really deep models yet. Also, we did not do a lot of skip connections and things like that. But it's very easy to use usually. So you just define your whatever complex is your favorite complex, and then you can even convert existing data sets to these complexes and get the Hodge Laplacians and all these operators, and yes, or simply define a cell complex neural network on it, and whatever you want. So, of course, it's a unifying library, right? It's kind of graphs, meshes, and point clouds. Doesn't really matter what you are doing. So you can apply it to different things. Well, even for actually graph analysis, we see that. So let's say if you have, I don't know, such a graph, right? This way, right? If you have such a graph, maybe one interesting thing that you want to consider, well, you can of course treat this as a graph and do all the GNN stuff, but you can realize you can just run a simple algorithm and kind of detect cycles in this graph, right? And you realize that, oh, there's a cycle. So maybe if there's a cycle, there is kind of you could convert maybe this to a face. This is called lifting. So you can take any graph data set, apply some kind of a simple algorithm to lift it in a higher order cell complex, okay, or combinatorial. And then you can use this library. And we actually did that. And even for graphs, we kind of get an improvement. But of course, there are a lot of very strong engineered architectures for meshes and graphs. We are only on par, and I think this is a good result. I'm hopeful about this because we don't do any specific operation. We don't know even how to do them, so it's great that we actually get something state of the art in these tasks. And so you can, well, of course, want to do diffusion models, for example, and it's the last thing I will show. Well, you can have a molecule, and you can kind of do this cycle tracing trick that I just mentioned, and then lift it to a combinatorial complex. And then you can easily define a diffusion model. So graph diffusion models are usually defined as diffusion models on vertices and edges. But now you simply have the Laplacians and adjacency matrices for all of these higher order Laplacians you have, or higher order neighborhoods you have. So simply just run your diffusion models instead of running on one Laplacian, you run it on multiple Laplacians. For one adjacency matrix, you run it on multiple boundary matrices. Right? So we tried it, and you can in fact get interesting higher order molecules. So you don't just generate the molecule graph itself, but you also generate the hypercells that they are attached to. And that's interesting because now you can speak more of the structure of the molecule. So it's a more structured recovery. I don't have a lot of quantitative results. This is just on par. We did not outperform any drug discovery benchmark yet, but there are some teams working on it. Some people are working on doing transformers, and some people are working on fusing this with other modalities, right? So maybe this is not the holy grail, but this is an added source of information to any other architecture you have, and so on and so forth.
So most of the structure is not the discovery, right? In the previous example,
so usually, this is, yeah, so yes, so here in the training data, the structure is given. and you learn it. You learn the diffusion model, and then, of course, you can run the diffusion model in a generative manner, and then you will generate structures. Yes. Yes, but of course, during learning, you need the structure. So one of the things that I'm really excited about, so you just give me graphs,
Yes.
and I would kind of detect the higher order structure as I learn it. So I only detect the higher order structures that are really essential. Maybe not all higher order cells are,
How
created.
is this stuff related to community detection?
Yeah, so there are a lot of, yeah, I mean, this is not something that I'm really interested in, but it's true that there are a lot of connections to that. Also, mathematically, there are connections to operator theory, category theory, and you all probably see a lot of category theory in there, which I don't know, so I wouldn't speak of them. Yeah, yeah, it's usually coming from algebraic topology, right? So there are also that type of connections, and people want to solve PDEs with those. Things like that, so that because you can model a more complex domain, how would you solve a PDE on this domain binary network? So these are all problems that I don't know, and they are still unsolved. So there are many open challenges if you want to. Yeah, I just listed some of those here. Yeah, I think I'm done.